So my talk today, I introduced myself at the very beginning of the day. It is, let me do that again. I'm Sharif El-Tawil. I'm a professor in the Department of Civil and Environmental Engineering at the University of Michigan. And my talk will focus on SRTI, which is a software that we have developed to enable interdisciplinary simulation of natural hazard scenarios. This is a topic that came up today several times on how to do this. And I'd like to introduce our own take on how we try to achieve this. So I'm making this presentation on behalf of a large group of people. The ones with the yellow boxes next to them are PIs for this project, and they come from multiple domains, from civil engineering, social science, and computer science primarily. On the bottom line are some of our very talented multidisciplinary students. This project was funded by the National Science Foundation under a Advanced Cyber Infrastructure grant. And if I go back to the opening remarks at the very beginning, some of the observations were that disaster science and engineering involve many disciplines, and computational models are well established in those disciplines, and we want to connect these models. But the problem is, and this was alluded to by multiple speakers, we want to connect these models, but they were never developed from the start to be connected. So if you can't do that, then you'd have to develop the models yourself, and you find yourself going into other disciplines to try and simplify them and create models so that you can use them yourself. But if you think a little bit about this, you see that users from one discipline do not need to know or have the training to know the details of the models from the other disciplines. Sometimes you only want a specific piece of information to transfer. For example, let's say you're a transportation engineer. You would like to know, did the building collapse and block the roadway or not? You don't need to know that the building itself collapsed and how it collapsed and any other details other than where did it collapse and how much did it block the roadway. So one of the tools and techniques in the computational world to deal with this is distributed simulation. Now let me define distributed simulation. And essentially a distributed simulation entails decomposing a large system into independent simulators that execute on separate processors or devices. It's quite similar to what a lot of the models that were discussed today. Now, where this, I think, differs from what was discussed today is in how this is implemented. So the very first distributed simulation tools that came out, this is one of them, distributed interactive simulation, has an IEEE standard associated with it. It was developed by the US Department of Defense. And the reason they developed that is they noticed they had models for planes and missiles and tanks, and they wanted to connect this all into war games simulations, and they couldn't because the models were developed by various groups at different times. So they developed this to try and integrate all of these together, very much like what we want to do in disasters. That was in the mid-70s to mid-80s. So from the mid-80s to almost the mid-2000s, this transformed into HLA, high-level architecture, which has actually a set of IEEE standards associated with it. Unlike the previous one, which had one simulator talking to another simulator, HLA organized things by having all the data pass through what is known as a runtime infrastructure. It's like a middleware, and I'm going to be talking about this today. Now, HLA is now obsolete, and the newest one is TINA, and it's similar to HLA in the way that it organizes its communicating messages. If you look at those three bullets, you will notice that they were developed by the Department of Defense, the US Department of Defense. These are open source codes. They're not secret or anything like that, but it's because of their own very specific need to organize their simulations. There are others, of course. There's distributed data services, lightweight communication and marshalling, LCM. We actually use LCM, and it is a software that allows robots that are in a swarm formation to connect with one another. And then Google has also version 2. So when we started our research several years ago, we looked at these different models, and we had certain criteria that in our mind that I'm not going to read them all. You can read them yourself on which ones should we be using and which are important. And you can see none of the tools, and I included Simulink here, the MATLAB Simulink. None of them had all the characteristics we needed, and so we decided, okay, we're going to develop this simple runtime infrastructure, and let's set down some specifications for it. So it has to be open source and free to use, similar to what we heard today from other speakers. It permits distributed simulations across multiple machines. We heard this concept also from other speakers. It supports different programming languages and operating systems. And this is where we differ from other approaches out there, because let's say you're in social science, your model works in NetLogo. You'd like to connect that to my model, which is written in Java. How can we do that? It uses a publish subscribe data transmission pattern. And this is how we can achieve this direct interaction between these simulators, and provides precompiled components to be downloaded and directly used without installation. We wanted this to be as easy as possible because we know that most of us are not very well versed in computer science. It uses data messages parsed as strings to allow the data to go back and forth. And we wanted to use strings specifically because they are easy for us as humans to read and write. They are easy for the machines to parse and generate. And so the data type that we selected in the end was JSON, which is JavaScript Object Notation. And most importantly, we wanted to be extensible and scalable to allow building levels of complexity that are not possible from what we could do before. So let me talk about some of these points. Publish, subscribe. The best way to think about this is to think of the middleware, the runtime infrastructure, as a pipeline or a set of pipelines in which data or water is being pumped in. So in this case, the scenario simulator, this could represent a city that is feeding information. All its purpose in life is just to feed the data. And it doesn't know anything else about this. If you would like to replace this city with San Francisco, all you need to do is do that. You don't care about what other simulators are using this information. Then next comes another simulator, the seismic simulator. It takes the data from the scenario and it knows where it would calculate the seismic signals using attenuation relations or any model of your choice. Next, you can add in your infrastructure system. Let's say you have a water system. This reads from the seismic simulator at the locations of interest to it, kind of how much, and then it calculates how much damage happened at this location, what is the performance of my simulator, and if my system is dependent upon another, let's say power, then you don't need an interdependency matrix. You can just look for the data that you need and keep going this way. As you can see, the number of arrows has increased a lot, and this is quite a complex simulation now already. You could do other things with it. You could actually now optimize, say, the recovery process by reading the data that is now coming out of your entire system. You can visualize it, look at it in a visualization simulator, or you could put yourself in the simulation with a joystick, disrupt things and see how things are. And when you're done, the next day you want to do this again, you download another city, and let's say you want to put in a building system for that, and you can connect it to your other infrastructure systems and look at the interdependencies that arise between them. So the key advantage of this approach is the extreme decentralization that happens, and that allows you to build complexity quite quickly. So next topic that I'd like to discuss is the distributed simulation across multiple machines. This was one of our very first simulations. This was a wind analysis that we did for a group of buildings, and each simulator that we had ran on a separate machine. They were all connected through a local area network, but they could have been connected over the internet. And because I showed you the data as a channel, it's not a linear channel. It is something within the computer that you feed data to and get it from. So it can work across the internet, and that gives also significant flexibility. Last one, achieves extensibility and scalability for complex situations. And this was alluded to by several speakers today. But let's imagine that you are talking at the bottom left here on the building infrastructure system. And all you wanted from it, as I mentioned earlier, is to know whether a building collapses onto your roadway and blocks the street. This is a simulation animation that I'm going to show towards the end of my talk today. The transportation engineers that are trying to use your model, they don't care how you got it. You could have gotten it from a Hazus equation all the way to a sophisticated 3D finite element model. Of course, your answer is as good as your model, but that separation of the disciplines or that separation of the trades is quite helpful in situations like this. So there are two products that came out of our project, version 1 for the SRTI and version 2. Version 2 is no better than version 1. It just needs more expertise to use. And so that's why we consider it to be separate. But the main components are the user simulators at the very bottom. These are written in different languages. And for you to connect them to the middleware, you have to use certain libraries that we have developed, APIs, application programming interfaces, And once you incorporate those in your simulator, then now you can read and write, subscribe and publish data to the server. The server also has a graphical user interface that tells you, like, is the data being pumped out, where it's coming from, where it's going, just to make sure that you can debug as you go through. So the three components that I'm showing here in orange, like the 3 levels, these are all pre-compiled. You don't have to compile them. And that increases the usability of this, because you don't have to worry about compiling data, the error messages you get. And our hope is that this democratizes the software. Going across between all of these components are the JSON object data that's going back and forth. Now, this needs some expertise, because the simulators are triggered in a way that you as the user would have to control. And this is where the expertise comes. Do you wait for your simulator to trigger when it gets a certain message, or do you tell it to trigger at a particular time? And you have to have some level of control and knowledge to be able to do that. So version 2, which is we consider to be for general users who have less computer science knowledge, this one has a different architecture, and it has the same server, but the RTI server, the runtime interface, has a config file associated with it. That's a text file that you can edit, and you can allow it to get the management logic there. So instead of leaving it to the user, it is put in this management logic, which comes from a graphical user interface. So, and the graphical user interface writes this config file for you. And I'll show you an example in a second. The other innovation are the wrappers. So the wrappers are a piece of software that is written to allow you to communicate between your simulator and the infrastructure in a very simple way. In the previous, in version 1, you had to incorporate that into your code. But here, you don't have to do that. Your interaction happens through a config.json file, which is also a text file that you can edit if you're an expert user, or the graphical user interface can write for you. So just to give you an idea of what the GUI looks like, it's a screen divided into multiple pieces. On the left are your simulators. So you can grab simulator 1, 2, and 3. This one is written in Java and C++ and whatever, and that logo. You can then drag them into the simulator canvas, and the way you place them triggers how they are going to work. So if you put them at the same level, they're running in parallel. If you put them in different levels, they're running in series. And you can see the red arrows here and here. These are arrows that describe how the data is going in and out of the channels, which is on the message canvas. So you can again debug your scenario modeling this way. The inspector panel allows you to set certain parameters if you wanted to on when certain parts of the analysis started or stopped. So I'd like to show 2 examples of this SRTI in action. The first one is the seismic resilience of a power network. It is set in Shelby County, which is quite famous in the hazards research community, just because data is well established for it. This is an 800 square mile region with almost 1 million people living in it. And so in this case, we assumed that Shelby County was going to suffer an earthquake with 7.7 magnitude and a specific location on the left. We're using attenuation functions to then, through this seismic simulator, to send the data to wherever it's needed. On the top right is the power supply infrastructure. It's showing the various gate stations, the substations, and the nodes and transmission lines. That is the first example. In the second example, I'm going to add the building infrastructure, which is another 300,000 buildings with different materials, structural systems, construction errors, and occupancies. And then we would like to look at the interaction between them. So this is example 1, and this is the kind of simulators that I have selected. The analysis progresses in stages. So on the left here, you can see they're color coded. So first one, stage 0, is initialization. This is the scenario simulator shooting out its data into the pipeline. It's now available for anyone to read as they need it. The first stage, stage 1, and this is the disaster occurring. This has a time step of 0.01 second. So as the disaster progresses, you're calculating the seismic signal, the damage to the network, and the network performance. And you can see that the network performance on the top here has two colors. It's green and yellow because it spans or straddles two stages. So I'm going to skip the gray stage because this is not appropriate for here. It's appropriate in the next example, but the time step is 1 day. So as you step through time, now you're looking at how you recover and what strategy you're using. As Professor Van de Lint mentioned, like this could be policy decisions. I'm going to fix all the most expensive parts first, or I'm going to fix, spread my resources evenly across all the damage zones. So you can explore some of those things. And of course, you can pull out your data and look at it in a visualization mode. So if you did that, this is kind of our very first NetLogo visualization simulator. I'm not showing it as a video here, but these would be flashing red and green and blue, showing the various components of the system getting damaged and then coming back online again. Now, I go back again to the beginning, which is the electrical system. But now I'd like to load my system with the building infrastructure and the people that are making decisions within this system. So all I need to do is pull out the right simulators and add them in. They're still color coded, but I've added the building infrastructure over here. And I'm adding the people and the casualties associated with that down here. In gray are some of the decisions that are made by the people that are in these buildings, and the other parts remain the same. And this also continues to use the publish subscribe principle. I would like to, and I'm not showing you details here because if you don't like what I'm saying in terms of the details for a particular simulator, you're welcome to bring your own and plug it in. And I'd like to talk about one of them, and that's the household decision simulator. So after a disaster, people living in the buildings in the disaster zone are faced with a decision. Do we demolish and rebuild? Do we repair our home? Or do we leave the community? And we've selected the smart decision-making algorithm to help us make that decision for our agents or the people or avatars who are living in those buildings. And SMART is just a collection of factors that are then weighted in a certain way. And the agent, the person, is collecting this information in their head and adding it up, and it's giving you a number. That number, depending on how high it is, then takes precedence, and the highest number then determines which decision to take. What goes into the smart decision-making algorithm comes from other simulators. So for example, the scenario simulator provides data about income, ethnic minority, construction age, do you have insurance or not? The power simulator tells you if you have power or not. So if you're in your home, it has been severely damaged, you don't have power for a long time, you might think of abandoning this community to go somewhere else. So all of this information comes together, and then the decision is made for that particular agent. So just to show some data, again, you can critique this, that it's not very realistic or whatever, but the thing is, you can put in your own simulator models that are better than the ones that we have used. And in this case, I'm just showing the distribution of building damage, and I'm close to getting done here. You can see that the buildings that are closer to the epicenter are more damaged than they are farther away. You can also see that the repair cost towards the end, there are many buildings that got totally destroyed, and so these are going to have 100% replacement cost. And as all this data goes towards the agents that are living in the homes, they're basically deciding on what to do. And you can see here on the left side are the number of homes that have made the decision to repair or rebuild or abandon. In blue is the decision without the power network, and in orange if you had the power network in place. So that's the interdependency between the building, the human, and the power network there. And you can see there are some differences. So you would abandon, you can see that more people are deciding to abandon if they knew that their power would get disrupted, for example. Again, the type of model that you put into your simulation affects the quality of your result. But that's true of any type of simulation situation. And the flexibility and ability to be able to connect these models is the primary advantage of what I am discussing here today. So once your analysis proceeds, you can take the data and you can look at it, just like I showed you before in a very simple simulation. But if you you could be much more sophisticated than that. So in this case, you can see the buildings are shaking. This is actually in virtual reality, so you could be wearing a head-mounted device and looking at this. You can see there are cars that are coming and now they have to stop because the building completely collapsed. This is a 12-story building. It's really weird that the people don't care, they just keep walking. But we're still teaching them what is right and what is wrong. So, but within virtual reality, you can then fly up in the air and kind of get an idea of what the overall system looks like, what the city looks like. You can go back down again, and it's pretty awesome to be standing underneath a building as it is collapsing, or as it's collapsing on another building and causing that second one to also collapse as well. Now, just to conclude, I just introduced the Simple Runtime Infrastructure, which is a software for distributed simulation. I will not read its characteristics. I think it's there for you to check out, but this could be used for other fields as well beyond disaster research. I would like to say that I'm going to jump to the very last one, which is that there's a hands-on workshop between 4 and 6 p.m. today to show how to download and set up SRTI. There, we're going to go through examples that I showed today. The simulators will be available to you and you can take them and play with them. Our goal right now is to build up this simulator library so that others in the future can just come in and build upon them and or add their own simulator so that other people can then build complexity upon complexity. For those of you in structural mechanics, the simulations that I showed today are in the Euler sense, meaning that you just take a step and then take another step without really looking back. But we have done cases where we have done it in a predictive, corrective, or incremental iterative scheme, where you go forward, see what happens, and then come back again to ensure certain types of analysis progress. So there's a lot of exploration that now we're doing with this system. And with this, I would like to thank you for your attention. And I think we can transition to the questions now. So I'm going to read some of the questions that have come up. So Ahmed Abdelhadi is asking, thank you for your presentation. Talking about simulations across many disciplines to quantify community resilience impose large computational runtime. How does the SRTI handle this computational challenge? And is it possible to run SRTI on a high performance computing environment to accelerate the runtime? So yes, you can run it on multiple machines, and each of those machines could be linked to multiple cores that are running in parallel. There's no problem there. The highest time consumption is in the transmission of the data. That is where we have the least control. And as I think someone mentioned today, I'm sorry, I forget who, the latency, I think it was Professor Sextos, between the US and England was about 100 milliseconds. So when you're sending a lot of information between the various simulators, that's where the delay happens. The more the information, the more the delay. But we figured out that it is more important to be able to collaborate with people in different fields than to worry about the run time that is needed in order to go there. So another question, how are the output decisions from SMART validated? And this is also from Ahmed Abdelhadi, and they are not at the moment. What we could do is we could do a hindcast like what Professor Van der Linde did. This is just currently based on information that we have. We could do surveys. But again, the point of my presentation was not to show the specific research results, but what can be done with it. And so if the SMART model is not working for you, remove it and then put another one that can do the job in perhaps another way. From David Bonowitz says, sorry, the SMART slide went by too fast. Does the SMART algorithm account for decisions made by social network leaders or peers? That is my decision based in part on what others already decided to do, or is it based only on objective data? No, it does not. It is not based on other agents that are living near to you or network leaders. It is based on the specific parameters that are available to only the person living in that house, the head of the household. However, if you had information from others, that could be incorporated into the SMART decision-making algorithm. Right now, we incorporate 12 parameters, but it could be 15 or it could be more as you add other parameters that influence the decision. I want to make sure just I remain on time. Okay. So Safa Al-Rih says, we can set up different modules to run sequentially or in parallel. Are there options to set up conditional sequencing for these modules? Yes. So within your config file and the way that you set it up, yes, you can definitely do that. So you have a lot of flexibility in running these simulators and when you need them. Navid Atari says, thank you for the great presentation. I appreciate that. 2 questions. The way you set up the SRTI, is there in any way to consider the interaction between different components? For example, combining structural analysis part and the hurricane part. Yes, definitely. And that is the entire intent of this, is that the hazard simulator tells you what the hazard intensity is at various locations. Then your structure simulators can come in and subscribe to the data and know what the intensity is and then react to that intensity. So definitely this is one of the motivations that by which we developed this software. For Shelby County, the power network seems to be in a substation level. How was it distributed to buildings for recovery estimation? We assumed that all the buildings in the zone around the substation were affected by that substation. And so we did not differentiate between one building and the other in terms of the power availability. As long as the substation was okay, then the buildings around it were okay, or vice versa, the opposite. Let's see, Mariam Akram says, thank you for the nice presentation. Can you please give more information about the flow solver of SRTI? Also, how detailed are the city structures implemented? So the flow that happens within SRTI is handled within the software itself. It automates the messages going back and forth between the simulators. That's the primary innovation in what I'm talking about. And that is a key idea behind distributed simulation. How are the city structures implemented? They're just data. So we've made many cities, small ones, big ones, thin ones, long ones, based on kind of our requirements. So a city would have roadways, it would have people, it would have buildings, and this is all within the scenario simulator that's being fed to the simulation. I think there's other questions here. So from Dr. McAllister, how do the individual simulations inform each other, such as exchanging the data for interaction between the physical and social systems or impacts? So that is what happens with the publish subscribe principle. When a simulator is done with its data, it publishes it into its channel. And then another simulator, let's say it is a person simulator that is seeking to do something with this data, like make a household decision. It would then subscribe to this data and read it and do something with it, and then it can publish it again. So this removes the sequentiality that I think plagues a lot of maybe the algorithms that exist out there. You can do things in parallel, or you could do things in series. And I think that is one of the particular strengths of this. Like I mentioned, one of the weaknesses is the speed, because this data transfer takes time. And for very large systems, like I talked for the 300,000 buildings, it takes a few seconds for it to go from one step to the other to be able to do that. Right? Thank you very much.